In 1994, physicist Miguel Alcubierre wondered whether the fictional concept of a faster-than-light warp drive, such as the type depicted in Star Trek, could be described with the real physics of general relativity. Alcubierre took Einstein's field equations, shown here, and did something rather unusual with them. Usually, one takes a set of masses and energies whose distribution is described within the stress energy tensor on the right-hand side, T mu nu, and then one calculates the corresponding curvature of spacetime over here on the left-hand side. But Alcubierre did the opposite. He started from a particular geometric structure, G mu nu, specifically in his case a warp bubble, and then solved the corresponding masses and energies needed to make it happen, T mu nu. His solution, often called the Alcubierre drive, has forever immortalized his name and sparked dozens of follow-up papers further investigating this topic. However, it's not really a drive. There's no blueprint for a spaceship here. Perhaps a better name would have been an Alcubierre solution or a field, but for whatever reason the name has stuck, and so I will use it throughout the rest of this video just for consistency. Alcubierre's solution involves a central region where passengers would reside of ordinary flat spacetime. Behind them, the fabric of space expands though and pushes the passengers forward, much like how the universe itself is currently expanding, thereby pushing galaxies apart from one another. Inside the bubble, the passengers can be stationary, yet the space within which they sit is moving, almost like an airport conveyor belt. So how do you warp space? Well, we already know that. It's through mass, the same way that the sun bends space, as Arthur Eddington proved in 1919. But here, a carefully engineered ultra-thin shell of material is used, much like an eggshell, that keeps space-time undisturbed both inside the bubble and far away from it. And yet, it distorts space-time in just the right way around the ship. The real genius of this idea is that although mass cannot accelerate past the speed of light, space itself has no such rule, and thus this central region containing the passengers could travel at arbitrarily fast speeds. As exciting as this is, we need to take a beat, because the fact that a solution exists does not imply that an Alcubierre drive is actually physically plausible. And yet, general relativity does not forbid such a machine. And so, there was hope. However, this is one of those topics that gets sensationalized out of hand here on YouTube, and it can be difficult to figure out just how legitimate this idea is. So today, let's go through 6 of the most prominent obstacles to realizing Alcubierre's drive, coupled with some thoughts on how feasible it is that we could solve each of them. So join us for the complete guide to the Alcubierre drive.
Let's punch it.
Problem 1. Energy and mass requirements. One of the first complaints levied against the drive was that it required outrageous amounts of energy. For example, soon after Alcubierre's paper, Fenning and Ford estimated an energy requirement of something like 10 orders of magnitude greater than the mass of the observable universe. But in 1997, Chris van der Broek slightly modified the warp bubble shape to pull the energy down to just 3 solar masses. Okay, this is still a ridiculous amount of energy, but I remember reading those papers as a teenager and being incredibly inspired to become a physicist, because in the space of just 3 short years, pure human ingenuity had reduced the energy demand for a warp drive from 10 universes to just 3 stars. So imagine what might be possible with further refinement and research. Surely we could get this down to practical levels. Another issue is that the actual shell of material needs to be incredibly thin, typically approaching the Planck length in width. The Planck length is thought to be the smallest measurable length, and at this scale, the universe itself is believed to look more like a quantum foam where known physics breaks down. So how severe of a problem is this? Despite the currently incomprehensible challenge of humanity ever reaching this kind of technical level, as far as we can tell, physics does not prohibit it. And so, I think we would have to classify this as an engineering challenge, just an engineering challenge of unimaginably high sophistication. Problem 2. Exotic matter. Whilst we're on the topic of energy requirements, there's one minor issue I forgot to mention. We need negative energy, or interchangeably negative mass via equals mc squared. This was a problem recognized right from the outset of Alcubierre's original work, and technically violates a rule in general relativity known as the weak energy condition, or WEC. That rule states that all time-like observers must see a positive energy density. By the way, a time-like observer here means one who always moves forward in time and experiences a natural flow of time, similar to our own everyday experience of time passing. To give some credence to this violation, Alcubierre himself even wrote his only warp drive follow-up paper 27 years later that supports and explores this violation in much more detail. Violating the weak energy condition implies the existence of negative energy or mass. Now, unfortunately, we don't know of any particle with negative mass, but physics also doesn't prohibit one either, and hence such a particle would be described as exotic matter. The Casimir effect is a well-known example of a negative energy pressure caused by the quantum vacuum effect between two very close plates, and it has been the lifeline of hope for many warp optimists. However, it's important to note that this is really a negative relative to the background vacuum energy. If you took that vacuum energy away, there'd be no negative, so it's unclear whether this could be utilized for warping space. The widely held belief that Alcubierre drives violate the weak energy condition was challenged in a trifecta of papers in 2021, coming from Bobrick and Martyr, Fell and Heisenberg, and finally, Eric Lentz. Whilst this confluence of timing might seem strange, it's worth remembering that this all happened around the time of the COVID-19 lockdown, and Lentz stated in an interview that this is what he spent his lockdown working on. In that work, Lentz splits space-time up into many layers and then uses hyperbolic relations to model their rapidly evolving states, unlike what Alcubierre did in 2017, who used a more linearized approach. His solution looks quite different, involving diamond-shaped regions formed by layers of rings and disks made of super-dense fluids similar to the interiors of neutron stars. But before we get too giddy with excitement, not everybody agrees. Just last year, Jessica Santiago and colleagues pushed back that these papers are all mistaken. They argue that what these papers accomplished is to find a positive energy solution for one particular choice of observer, but the weak energy condition demands this to be true for all time-like observers. And indeed, they further conclude that all three of the proposals certainly do violate the weak energy condition when examined more carefully, and further, this is sadly a generic feature of warp drives more broadly. I want to note that Lentz disagrees with Santiago's rebuttal, but I think it's fair to describe this issue as controversial for the moment, and so we may be back to clinging on to some kind of Casimir-like effect for any kind of hope here. As you can tell, the literature on warp drives is surprisingly extensive, and of course this is just one small topic within general relativity, physics, and science more broadly. It's easy to feel overwhelmed by all of the things that we wish that we had the time to learn and read in our all too short and fleeting lives. But fortunately, that is where the sponsor of today's video can come to the rescue, Blinkist. If you struggle to finish non-fiction books, need good recommendations, or simply don't have enough time to read everything that you want, Blinkist is a professional book summary service that allows you to grasp their key concepts called blinks in just 15 minutes or less. A recent highlight for me was Uncharted by Margaret Heffernan, who explores the inherent unpredictability of the future, the value of scenario planning both for corporations and in our own lives, and the role of cathedral projects like CERN that can span generations. There's also a Blinkist Spaces, where you can share books with families and friends, even if they don't have a premium subscription. So I think this is a really cool product. You can get started with a 7-day free trial and then 25% off the Blinkist annual premium package using my promo link down below in the description. Thank you to Blinkist for sponsoring Cool Worlds today. Problem 3. The Horizon Problem. Soon after Alcubierre's paper, Sergei Krasnikov pointed out that the occupants of the ship would have no way to control, steer, or stop the vessel, or indeed interact with the outside world in any way. An observer located at some initial time cannot affect points outside of their future light cone, which would be required to affect the front of the bubble. Photons produced by the crew, say in an attempt to interact with the front side of the bubble, would simply pile up as they approach and remain at rest relative to the bubble's motion, never quite reaching the front. The consequences of this are fairly profound. Anyone or anything inside a warp bubble cannot control or indeed even create the warp bubble in the first place. After all, any energy field they create inside here cannot reach the front of the bubble, which of course where it needs to be to create the bubble in the first place. This situation is analogous to the concept of horizons in cosmology. If one passed through the event horizon of a black hole, there is no way that one can ever interact with the universe outside that. And so this is why the problem here has often been labeled as the horizon problem. This problem suggests that an FTL Alcubierre drive is not realizable as an isolated entity. We would always need some pre-existing infrastructure built ahead to enable this kind of travel. Like an interstellar highway, we'd need some kind of gigantic tube with negative energy field generators located all the way along it that turn on at just the right moment to create the bubble effect. Perhaps like the huge energy requirements issue we discussed earlier then, we might generously describe this as an engineering problem rather than a fundamental obstacle posed by physics. Problem 4. Radiation. As if the horizon problem was not worrisome enough, it unfortunately culminates in another issue though, radiation, explored in a recent paper by McMonagle and colleagues. Imagine a photon happily going along its way through the universe when from the rear, the FTL Alcubierre drive catches up to it. Like a snowplow, the photon gets caught in the front of the bubble and dragged along at FTL speeds. Curiously, if we replace the photon with a near light speed particle or even an astronaut, they would become time-locked for the duration of the warp flight, frozen in place and experiencing very little time passage. Unfortunately, when the ship eventually stops its destination, all of the particles that got caught in that front scoop suddenly get released, and they do so with far more energy thanks to the bubble's motion. The energy dump is so huge that it's sufficient to completely obliterate entire planets, which, let's face it, I don't think is quite how Picard imagined rocking up for those peace negotiations. Of course, this danger could be mitigated by simply stopping outside of the target system and then continuing the rest of your journey at sublight speed, so this problem hardly prohibits the warp drive as a concept. Something much more concerning is what goes on inside the warp bubble. As a horizon, Hawking radiation will be generated due to quantum pair production effects along the rim of the bubble. Finazzi and colleagues investigated this in 2009, showing that the radiation will have a thermal temperature set by the surface gravity of the warp bubble shell, which, recall, has a width approaching that of the Planck length. As a result, the thermal flux incident upon the ship and her crew is of order of the Planck temperature, a staggering 10 to the 32 Kelvin, a temperature not seen since the Big Bang itself. Finazzi concludes that this leads to a completely unstable system, and the warp bubble would almost immediately collapse as soon as it was created. This seems to be a very severe problem, and the only hope I can see here is that an alternative warp bubble metric can be one day found that reduces the Hawking temperature dramatically. Problem 5. The chicken and egg problem. A series of papers have argued that a fatal flaw with the idea of a superluminal warp drive is that one needs one to make one, a catch-22 situation. The Alcubierre metric g mu nu is a warping of space, but even if one achieves this warp bubble, that does not equal a superluminal warp drive. In 1998, Cole argued that in order for the space-time geometry g mu nu to be moving superluminally, the matter distribution inducing it, T mu nu, must first also be moving superluminally. This conclusion was also supported later by Chris van der Burg, who clarified that at least some of the exotic matter must be moving faster than light. The problem is that in order to cause the required warping around this inner protected region of flat space-time, some of the exotic matter must necessarily be outside of that inner region, and all matter outside of that inner region must move slower than the speed of light. The effect of this is that part of the necessary exotic matter will not be able to keep up with the rest of the bubble. If somehow we did get a bubble that was moving superluminally, the outer shell would be left behind and thus destroy the warp effect. Kuhl seems surprised that Alcubierre was unaware of this issue, and van der Broek even states that Alcubierre spacetime is an example of what can happen when the Einstein equations are run in the wrong direction. However, van der Broek speculates that it might be possible to get around this problem by allowing the distribution of exotic matter to expand and fan out into a tail at the back, almost like an exotic matter contrail, but it's unclear whether this is even possible. In the most recent paper along these lines, Bobrick and Martai highlight that the majority of the literature generally assumes that the required curvature of space is already moving superluminally, which again raises the question as to how that could be caused without some matter distribution, T mu nu, that was already superluminal. Indeed, in a 2021 interview with Scientific American, Bobrick says none of the physically conceivable warp drives can accelerate to speeds faster than light. Is there a way to save the Alcubierre drive from this problem? One obvious solution is just to surrender the idea of FTL travel and stick to subluminal warp drives. In this case, there's no catch-22 since we can already in principle accelerate objects to any sublight speed we want. Another solution is to surrender the idea of a self-contained ship, and certainly alternatives to the Alcubierre drive do exist, such as the continuous tube of warp spacetime proposed by Sergei Krasnikov, and similarly we have the Einstein-Rosen wormhole concept, topics that I'm happy to get into in a future video. But the point is that in either case, our current understanding here prohibits the idea of a self-contained, faster-than-light warp drive. Problem 6. Causality. The final problem I'll discuss is causality violations, which really means that the warp drive can create closed time-like curves, CTCs, that is to say, backwards time travel. The problem here is that such a machine could potentially create paradoxes, such as the famous grandfather paradox, where one uses the warp drive to go back, kill one's grandfather, and thus meaning that you could not have traveled back in the first place since you were never born. Bizarrely, general relativity does not forbid backwards time travel, but it seemingly breaks down the predictive capacity of physics and makes many of us deeply uncomfortable. Stephen Hawking suggested that it was indeed impossible because of his famous chronology projection conjecture, arguing that whenever one attempted to use a time machine, quantum effects would prevent this from actually happening and would somehow destroy the time machine or prevent the paradoxes from forming. Hawking's conjecture wasn't idle speculation, but grounded from a strong mathematical argument concerning feedback. Like putting a microphone too close to a speaker, the same signal can whip around many times, increasing in intensity exponentially and ultimately destroying the time machine. So how does a warp drive lead to time travel? First, this is not some sort of time dilation effect, since by construction, the passengers can actually be at rest in their own little inner protected pocket of flat space-time. The time travel effect here is a subtle and complex topic which deserves its own video. Unfortunately, we have already made that video, which you can find up here. To try and keep things simple, that video shows why FTL violates causality in the framework of special relativity, but the manifestation of closed time-like curves occurs even in general relativity, as proved by Alan Everett in 1996, soon after Alcubierre's original paper. I think there is a lot of confusion about this topic, but I want to emphasize that Alcubierre himself acknowledges that his drive is a time travel machine. For example, he says so as much in a recent interview over on Event Horizon with friend of the channel John Michael Godier.
And there's a proof, a general proof, that any method you come up with that allows you to travel faster than light can in principle be turned into a time machine. That's true of the warp drive. I didn't prove it myself, but I hinted at it in my paper, and somebody proved it about a year later. Somebody actually proved it in detail.
Similarly, he stated in his lecture slides on the topic, beware, in relativity, any method to travel faster than light can in principle be used to travel back in time, a time machine. Further, he included a derivation proving this point in his 2017 follow-up paper, and he has stated the same thing on Twitter in interactions with other scientists. So, sadly, yes, our current understanding is that closed time-like curves appear to be an unavoidable feature of FTL travel. However, that does not necessarily rule out the possibility of a warp drive. For one, Hawking's conjecture could be wrong. I mean, it is unproven, or perhaps it's something more like the Novikov self-consistency principle, which we've explored in a previous video on time travel. Alcubierre himself has pointed out that even if Hawking's conjecture holds, the warp drive might still be possible though, since one doesn't necessarily have to use it as a time machine, even though, yes, in principle, one always could. Indeed, perhaps it's only in cases where you attempted to use the drive in this nefarious way that the conjecture comes into effect, perhaps instilling some kind of quantum feedback effect that destroys your warp bubble. It's difficult to imagine practically how this would work, so I remain skeptical this is a way out here, but perhaps it provides a glimmer of hope to some of you. So there you have it. 6 problems that stand in the way of an Alcubierre drive. For some, like the energy requirements and horizon problem, we can perhaps argue that these are merely engineering issues, but for others, the problems are more fundamental, such as enormous radiation levels, violating both causality and the weak energy condition, and a catch-22 problem. Interestingly, almost all of these problems go away when dealing with subluminal warp drives, which would still be a remarkable achievement where the rate of time passage could even be controlled within the bubble itself. For me, I take 2 things away from Alcubierre's drive. The first is inspiration. I may not have even ever become a physicist was it not for his paper, and I think many others feel similarly inspired. But not just by his work, but by the many papers that followed, incrementally improving the model and also revealing the fundamental problems with the concept itself. His idea is an intellectual playground that we can't help but have fun with. The second takeaway is that the challenges here are so formidable that it seems highly unlikely anyone will ever build one on Earth or even beyond. To make it happen requires multiple new physical possibilities to be revealed that all fortuitously work in just the right way that we need for this to be possible. It's frankly akin to hoping for magic at this point, but magic that just so happens to work in the way that you hoped it would. To some, that might seem depressing, but the truth is that interstellar travel is perfectly possible without a warp drive. It just comes at the cost of relativity, like time dilation effects, or simply a lot of patience. But looking for shortcuts, tricks, and cheat codes to the universe might yet reveal a way for us to touch the stars one day, and Alcubierre's work will surely be remembered as one of the most audacious and exciting ideas along those lines. So let's keep looking for those opportunities, those loopholes, and as always, stay thoughtful and stay curious. Hey you, I hope you enjoyed this video. If you did, be sure to subscribe and let me know what you think down below in the comments section. And if you haven't already, you can check out the Cool Words podcast using the link down below. If you really want to help out my research team, one way to do so is to use the link up above where you can become a donor, just like one of our latest supporters, that is Yon Williams. Thank you so much for your support. So have an awesome day out there, and thanks again for watching.